This video is about how to use a remote control with your Raspberry Pi so that you can use the remote control like for a model aircraft and before they go to the servos, read it into the Raspberry Pi. So this is a servo tester. It gives a PWM signal and I can turn the servo tester and the Raspberry Pi exactly reads out the PWM value. It's with a precision of like 2 to 3 microseconds deviation. So it's really precise. And to get it this precise, I will show you how I did it and what the tricks were. At first, about the wiring. I supply the servo tester with 5 volts. So basically on a model aircraft or model boat or model car, you will get like a battery voltage, and your ESC is sampling it down to 5 volts. And they go into the servo tester or into the remote control. The neutral position is 1500 microseconds pulse width, and then I have the ground connected with the ground and the 5 volt power supply connected to the 5 volt power supply. And then I used GPIO number 18 with a simple resistor and put it directly into the signal pin of the servo cable. So a servo cable basically looks like this. The black one is ground, the red one is voltage supply, and the yellow one together with a resistor can go into your GPIO pin. To the software. The software is quite simple. At first I have my pin is 18. I use the Raspberry Pi GPIO library. I initialize the BCM GPIOs and I set up pin 18 to input pin with a pull up. Pull down should work as well. Then in a loop we have like cycles of 20 milliseconds for the servo, and in each cycle there's a pulse going from 0 to 1 and which lasts from 1 to 2 milliseconds. So at first I am waiting until I get a rising edge. In the previous version I tried it with like these interrupts, but the interrupts are really slow. I'm better off when I'm using the loops directly. To save energy, I'm using the sleep command, more on it later. So I'm waiting for the rising edge. Then I capture the time. Then I'm waiting for the falling edge. And I'm capturing the time again. And then I multiply it with 1,000,000 and add 10. 10 is like a constant with what it needs to take these timestamps, so on. You have to figure it out. But if I add 10, I get quite exactly the value from the PWM servo tester. So why do I sleep 0.017 seconds? Well, this tells the operating system to idle, so I don't use more energy. So this loop only spins like about 3 milliseconds in this 20 millisecond cycle. So it's really energy efficient and still like 100 times more exact than the interrupt method. And then there's another problem. If the GUI or some other programs are running, sometimes the scheduler is busy. And to avoid this, I have to do a trick. At first, I have to edit boot command line and have to add the line isol CPUs equals to 3. So if I open boot command line, I add isol CPUs equals 3, and this will have the following effect. The scheduler of the operating system will schedule tasks to CPU 1, 2 and 3. The fourth CPU, which has the ID number 3, will never get any tasks, so the Python program which does the spinning loop will get all the resources of a whole CPU core. That's needed for the exact value, and then I have to correctly initialize. I use the following command. A nice -20 sets the highest priority, but we don't need this command since we are the only task on the CPU. And we use task set -c 3 to tell the operating system that this program must be scheduled on core number 3. So that's the whole trick. I will add it to the comments and upload the whole source code as you know it from me to my GitHub project folder. So let's spin it once again. So there's a little delay, but this delay does not come from the program itself. It's just the user interface is too slow, so it does not render fast enough. Okay, that's it for today.